Good morning or good afternoon. Today we're going to walk through the basic three-sided market model we've created as per popular demand, kind of translating an actual business problem into a cadCAD model. So what we have here is we have a LaTeX paper that we'll share as well as a notebook. I'll first walk through the LaTeX paper to understand what's going on here, and then I'll walk through the notebook. So what we have is a basic three-sided market that we're using Uber as the example here, where you have producers who are people with cars, and they're providing a service to the platform, which is Uber is the platform that's facilitating this transaction, and they receive fiat in return, and they use the platform. And consumers who want a ride, and then the platform facilitates the consumers and the producers working with each other. So the consumers obtain a service and pay fiat, and they use the platform. So we have there's three participants in this ecosystem essentially, which the Uber application, all of the market making essentially that they do there, and the producers and the consumers. So we represent this at a high level. We use, of course, we're just talking about cadCAD here. We talk about how we then go work on each individual component that we have in the model. So we have the growth curve. Essentially, we're saying there's a new business that's just starting. There's hardly any growth here, and then you start to hockey stick later, and then eventually it will be an S curve, and eventually start saturating the market. Then you have your cost function, which is like this is the marginal cost per ride on the platform, and you can see that it's more jagged and stochastic. These are, by the way, these runs are from 100 Monte Carlo simulations, and you can see over time that it kind of evens out, but it is still very variable. And then when you look at the simulation, we have the first group. It starts, we have cost of goods sold, R&D, fiat reserve, overhead cost, product cost, revenue, and then the investor money and transaction volume. And the last 5 of our Monte Carlo, you can see everything's changed significantly. And when we look at our results here, you can see our reserve balance starts with no money, and then it starts looking a lot better. Our seed inflow, which is essentially investor money that they've put into the system, is two cash injections, and then it stops. An overhead cost per month, every couple time steps, looks about every 12 or so, we're incrementing overhead costs by $5,000 per month. And then cost of goods sold, you can see the curve here kind of matches the revenue curve a little bit. So revenue's a nice S, same with transaction volume. Product cost goes down over time, as we were showing. R&D expenses per month, they go up periodically as well. And then we have gross margin per month and EBITDA, which is earnings before interest, depreciation, and amortization. Interest, taxes, depreciation, and amortization, which is good. These are great traditional business metrics, and they're going in the right direction. So when we slide up to our notebook here, we'll show how we built that. So this is how when we'll break down, we're taking a traditional S curve and we're looking at the last time step. We first just do it in NumPy before we do our full simulations. We can build these individual components based off of. We have a few different ones here of the curves showing. We get these types of curves off of adoption curves we've seen in industry research. We do economic research and things of that nature, so we are finding the individual components that then we link together. And this is one way that we model them, and here's how we're doing product costs. We're experimenting as well. So you have your parameters, you have with 36 time steps, and then you calculate here, we have some random stochasticness here, and then we basically iterate over them. These are not Monte Carlos, but we could just add a loop on top of it and save the results and add a Monte Carlo as well. So it's very easy and helps to get the intuitive nature of how these systems work together. And then our configuration file, we have our global parameters up here. And we have widgets in the dashboard. That's what these are doing. If this is a live notebook, we could use the widgets. And then we have the range, the number of simulations. This is the number of time steps simulations. We have a random state here. And then we have our exogenous processes, which is generate their transaction volume. We have our product cost generator. Those are in our, and we're seeing a little bit of cost decrease over time. In our model, those are external states. And then we also have investor money. We're keeping that as external. It's not part of the actual system of how the internal mechanisms of Uber operate. Of this very, very, very high-level abstract example, we have an update function for costs every 15 time steps, R&D as well. Our time model, we're saying every 30 days here. Then we have our behaviors. We're not doing agent-based modeling here, really. We're just saying, yeah, one means you're doing it, 0 means you're not doing it. And we have metrics, inflow, outflow, investors, and metrics. And investors, it will just say when there's an injection here. We have a little bit of logic. In the mechanisms, we have receive fiat, which we are adding the transaction volume times price here. As you can see, revenue, because it's a per month versus balance sheet account. Balance sheet account meaning that it stays the same. It's like a bathtub. You'll just change it based on inflows and outflows, versus this will start over each time. You're checking the rate of change, essentially. And then you have a receive fiat from investors, which is here. It's also an increase on the account. Then you pay product costs and all of those things. And then we wire them up. These are our initial states, and then we wire them up. Now in cadCAD, we can have a policy. There are no policies for exogenous processes. They just operate. Fiat inflow. We have the inflow, which it takes if it's a 1, it operates. We're basically abstracting out the agent-based policy methods. And then when we run the result, it's the same outputs you've already seen. We can see just a linear curve here. Coefficients. I'm just fitting a best fit line to kind of show there. And then we see the Monte Carlo simulations here, and those are the same results. So let us know if you have any questions. Hopefully this was helpful, kind of showing how we translate a high-level business idea into code and how we look at individual components before we wire them together and have the feedback loops.